Hi, in this video segment, I want to talk about intermolecular forces and heating and cooling curves. Now, when I talk about gases, or when scientists talk about gases, we often invoke what's called the kinetic molecular theory of gases. In this theory, molecules move, and it is an ideal situation. So it would be an ideal gas. Molecules move in straight line paths in random directions. The volume of the molecules is so small relative to the container that we call it a negligible or no volume. All collisions are elastic. That means there's no exchange of energy. And this is key. Attractive or repulsive forces are not considered. We're assuming they do not experience these. And this is really important. Temperature is a measure of the average kinetic energy of the molecules. So if you have the number of molecules and their kinetic energy, you would have what's called a Maxwell-Boltzmann distribution, and the temperature would be a measure of that weighted average of kinetic energy. So if you are measuring an increase in temperature, that means on average the molecules are moving at a higher kinetic energy. Now, as molecules get larger and as molecules get closer, all right, they start to go to the liquid phase and then ultimately to the solid phase because they get closer together and or their attractions get stronger and stronger, so they pull together tighter and they change phases. So if we look at that on a heating or cooling curve, this happens to be a cooling curve or heating curve, excuse me. A cooling curve would be just the opposite. It would start high and go low. So what we have here is heat that is added, or sometimes people will put time that a constant heat is added versus temperature. And we have 5 line segments that can happen. We can heat a solid, okay, and a cooling curve would be just the opposite. We can melt a solid. You can heat a liquid, so this would be pure liquid. This would be solid and liquid present. Then you can vaporize the liquid, and then you can heat a gas. And so this would be gas, this would be both gas and liquid. So 5 possible segments. In the gaseous phase, we have no intermolecular forces. As it begins to condense, so now I'm looking at a cooling curve, the substance starts to form intermolecular forces and become attractive as it forms a liquid. And so if you are looking at a heating curve, you're talking about breaking attractions. And if you're looking at a cooling curve, which would be the removal of heat, you're talking about forming attractions. Okay? Now, enthalpy of fusion, I wish they called it enthalpy of melting or something like that, but they don't. Enthalpy of fusion would be this energy that it takes to break. That's if we were melting, it's an endothermic or positive value, or the energy that is freed to form, that would be, when we freeze it, that would be exothermic or negative. That would be the enthalpy of fusion. The enthalpy of vaporization, caught a typo there, okay, is the energy that it would take to break. When we vaporize, it takes energy to break any force of attraction, whether it be an IMF or a bond. So IMF, it's molecular covalent. A bond, if we are talking about metallic, so network covalent metallic or ionic. Okay, and so that is going to be endothermic, or it's the amount that is freed to form attractions as they condense, and that is exothermic or negative. Okay, so that kind of gives you a sense of the overall picture of a heating curve and cooling curve. I'm not going to be doing calculations right now. I'm talking about this more qualitatively. Now let's look at what's happening here. As I heat a solid, these molecules start to move faster. And if they move faster, we're seeing an increase, and again, I'm going in a heating, kinetic energy, and that increase in kinetic energy is measured as an increase in temperature. Let me go to this segment. This is where I would be heating a liquid. So I would be increasing the kinetic energy of the liquid, and that would be measured as an increase in temperature. And finally, I can heat a gas, increase in kinetic energy as measured by an increase in temperature. All right. Now let's look at the phase changes. In a phase change, I'm either forming or breaking intermolecular forces. Intermolecular forces are an issue of potential energy. So you notice there is no change in temperature. What we're looking at here is potential energy primarily, not kinetic energy. And here, as we vaporize, we're breaking or forming intermolecular forces, or in the case of network covalent metallic ionic, we're talking about bonds. Okay, but the point is, attractions are about potential energy. Whoops, made that a little bit too big. Attractions are about potential energy. Okay, so we have a change in potential energy, not kinetic energy. So that's kind of a bird's eye view of heating curves and cooling curves. Let's look at, that had, by the way, the 4 of the 6 different phase changes on it. And a way you can remember whether it's exothermic or endothermic is I have my students ask what I say the stove question. Would putting it on the stove help? If the answer is yes, that means it needs the heat supplied and it's endothermic. If the answer is no, it doesn't like having that heat supplied, it's exothermic. But what about the other 2 phase changes? We have 2 more phase changes, and that's going directly from a solid to a liquid or back. And so here we have sublimation. We are breaking attractions, and we're going from the solid to the gaseous phase. All right, and that would be endothermic. Or we have deposition, where we're going from the gas phase to the solid phase, and that would be called, that would be an exothermic change. Now, the heat involved here, let's just call this the heat of sublimation, would be the heat of fusion plus my heat of vaporization. So it would be the sum of the 2. The heat of deposition is equal in magnitude but opposite in sign the heat of my sublimation. Right, one is exo, one is endo, but they're the same values. Okay, so that kind of gives us a bird's eye picture. In another video, we'll look exactly at the types of bonds broken and formed in these phase transitions as we look at the molecular level. Thanks for joining me.